Study a specific problem that we can give a very specific convergence analysis, and we'll define convergence in a moment. So this week we'll study this specific problem. So this is a quadratic function, like an analogy, in n-dimensional world. Okay. So this is a quadratic function, and for example, this is x transpose times is q, x subtract b transpose x, and specifically we need the q to be SPD. Okay, so i.e. q is symmetric and q is greater than 0. So and again, let's recall what defines like a matrix being greater than 0 is so we say a symmetric matrix Q and Q is a symmetric matrix. It means for matrix to be symmetric, this matrix must be a square matrix, because we can talk about whether its transpose is equal to itself. So it means for any D, B transpose QD is strictly greater than 0 for D in Rn. So if E is not the 0 vector. Okay. So this is a problem we'll be considering in this week's class. And in this week's coding assignment, that's going to be assigned. So we'll do something easier. So we'll basically, we'll use Colab, and we'll learn some basics of NumPy. And to prepare, coding assignment to, yeah, question. Notation, something confusing?
Can I have what Q SPD means?
SPD means symmetric positive definite. So SPD just means this. SPD means Q is positive and it's symmetric. And what it means for a symmetric matrix to be positive is...
Why are you working with this format of F?
Okay, that's a good question. So, the most simple example is linear regression. Think about this. Think about, okay, so X is our data. So for example, X is our data matrix. Our data matrix has n samples and capital N samples and the little n features. So so W is the weight we assign for each feature, and what happens is B is our target. Okay, so and what we want to do is we want to minimize this loss function. This loss function is, so this is our linear model, subtract our target, and we take square of it. Okay, so we minimize minimize this. Okay. So now we want to simplify this. So here I'm going to use one of my favorite notations for inner product, which I like to use. So we'll be using this notation in the rest of this week. That is, we'll use the parentheses. That is, so we used to use, so for two n-dimensional vector, so their inner product is defined as, we multiply each of their component and then we sum it up and we denote it as, so as the textbook I listed on the canvas, so we have two textbooks. One is Nocindo and Wright, the other is Chong and Zach. So both of these classical textbooks, you like to use this notation, but personally I like to use this notation most. The inner product. So this denotes inner product, normally denotes inner product in any Hilbert spaces, which we'll study all our optimization algorithm in. So, and once we use this inner product, the L2 norm, so if we only consider this, so we consider this as f of w, okay? So then, without the minimum sign, then f of w equals xw subtract b times xw subtract b, and this is nothing but like a middle school algebra problem disguised in like a graduate class, because this is nothing but a FOIL algorithm. So it's the same thing as x subtract y times x subtract 1. You know, so we learn how to simplify this in middle school. You know, but when we talk about inner product, it's the same. Okay, so this is xw times xw subtract xwb subtract b times xw plus bb. Okay. All right. So now what? Now we rewrite this guy back using the transpose notation. So what we have is xw transpose times xw. Okay. Subtract, and moreover we'll use what? We'll use the fact that the inner product is symmetric. So these two are the same. And we have this is 2xw 2b transpose xw. So these two are the same, and yeah, let me don't skip any step. All right. So and plus b and b are our target and b unknown, because these are data. You know, we talk about we have a pair of data. So our data is x and b. So this is our data matrix, and this is our target. And because b is known, okay, this is like a constant. So now we simplify this, we'll get, and we take advantage of, so if we have two matrices, we take transpose, it's this, so linear algebra, and we have, this is W transpose X transpose X. Okay. So subtract, this is what? This is B transpose. Subtract 2 times B transpose X. Okay, because matrix product has associativity, so it doesn't matter which two matrices, as long as the dimension match. Okay, the dimension matches, so it doesn't matter. It actually doesn't matter which. For example, this times this times this, we can either first multiply these two and then multiply this. If the dimension allows, we can also do, we multiply these two first and then this. And we can further, so this B transpose, sorry, this is B transpose B, and this is nothing but a constant, so we'll see in a moment. And now what we can do is we rewrite this as Q. Okay. So Q equals X transpose X. This is actually symmetric. Think about it. Q transpose is Q. Okay. So we take Q transpose. We have this matrix transpose. So it is. So the second matrix transpose first, and the first matrix transpose second. So X transpose, then we transpose it again, we get back to X. So, okay. So this is Q transpose is Q. And moreover, when we get rid of duplicate data points, okay, we can show, and none of the features, so we get rid of all the duplicated points, and all the we assume, like all the features are non-trivial, it means we don't have a data point that's all zero. Then we can show this is positive as well. Okay. But in general, this is positive. We call it semi-definite. But if we get rid of a duplicated data point, but this would be taught in statistics linear model class. I mean, it's out of scope for our class. We don't have to know this, but it's good to know this. Okay. So this will be taught in like a linear model statistics class, and the minimization problem, okay, of this type of stuff. So we'll see that because it actually corresponds to the normal equation. So the minimum corresponds to the normal equation. So the minimum is the solution is equivalent to the solution to the normal equation. So if we have taken the statistics class, it's a solution to the normal equation. Okay. To the linear regression problem. So if we have taken the statistics class, we may have heard of the normal equation. But thanks for the question. Yeah. This is our motivation why we want to study this type of thing. Okay. So think about so another thing is think about when we call certain optimizer algorithm, for example, for the most thing I'm familiar with, if we call, for example, we call a PyTorch optimizer, it has a toggle, it says weight decay. So if we set the weight decay, it's going to be non-zero, then this term will participate in the optimization. Okay. Anyway, let's study that problem. And so what we're going to study is first we're going to define convergence. What does convergence mean? So convergence means for our gradient descent algorithm, as we call gradient descent algorithm, so our gradient descent algorithm is for k is 0, 1, 2. So our next iterate, that is our x. So the textbook of the textbook of Nocido and both Nocido Wright and Trondak, they like to add a parentheses. They like to add a parentheses on top of the superscript. So let me explain the notation a little bit. So this is a x value at the kth iteration. for example, we optimize a loss function for a neural network. We update its weights iteration by iteration, and those weights are these x's. So alpha k is our step size. So in popular machine learning language, it's our learning rate. And then what the step size multiplied is the gradient of this f at the kth iteration. So it's this guy multiplied with the negative gradient vector as evaluated at the current iteration. So this is the gradient at the current iteration. Okay. So this is a gradient descent algorithm, and in this week, okay, so we're going to learn convergence and what are the necessary conditions for convergence for that simple problem, and how do we choose the step size, like, because we want to balance. Because this algorithm has this balance, okay? I mean, this is always a balance between the two. So we have the balance between the efficiency and accuracy. So if we want to get the most accurate local minimizer, we have to sacrifice efficiency, and we'll use math to demonstrate that. So I mean, this is like if we have done any project in machine learning, we know that, you know, if we want to make things most precise, we have to sacrifice something. But how do we tell this story in a mathematical language? Okay. So first, let's define convergence. So what does convergence mean? Is if, again, this x star is a local minimizer. Okay, so we defined local minimizer last week. So we talk about convergence is we say so in our class we say this x kth iterate converges to x star as k goes to infinity. So we say this convergence if is equivalent to say, so we're talking about it converges in certain norm. Okay, so there are lots of convergence in, so we're saying this convergence is convergence in a certain norm. So this is the convergence we'll be talking about in our class. There are other types of convergence, and we don't care about those. So there are lots of convergence that has weird properties in real analysis. For example, convergence in measure, convergence in distribution, but we don't care about those. So, but if you're interested in, for example, learning some Bayesian neural network or Bayesian method in machine learning, so convergence and distribution is also important. But this is what we're talking about. This is convergence in norm. Convergence in this norm. Okay. So this is a certain norm. It might be two norms. It might be one norm. It might be other types of norms. Okay. So this is a certain norm. So this is convergence. And so in our career of solving optimization problem, no matter in what field, we'll hear global and local, these two terms, like way too often. So I mean, in the past 2 weeks, so we have defined like local minimizer, global minimizer. Okay. So local minimizer, using English language to quantify it, it's basically like the lowest point in the neighborhood. Okay. So global is like the lowest point for all possible like values in our admissible domain. It's either Rn or some omega. So now what does it mean by the convergence? So this is like a dynamic procedure. Okay. So we have a bunch of iterates. What does it mean by a global convergence for this procedure? Is means, okay, so xk converges to x star as k goes to infinity, no matter what no matter what x0 is. All right, so this is global convergence. I mean, using plain English to translate this, okay? So it basically tells us our algorithm converges. See, by algorithm I mean our gradient descent algorithm. Our algorithm converges no matter where we start. Okay. So later, maybe today, maybe next time, we'll see that for a quadratic function, okay, right here, that Q is SPD, then we have global convergence. So if we choose the correct step size or correct learning rate.
I have a question. The k is the iteration.
Say it again.
So x to the power 0 is the k. It's equal to infinity. What the k represent the iteration? The k.
So k is dynamically changing, right?
Yeah.
So k is like 1, 2, 3,
Okay.
but
So
when k goes to infinity, our iterate converges to local minimizer.
Local minimizer. So no matter what x is 0, what does that?
This. Okay. So here. So x0. So x0 is our initial point. So
yes.
This is not thanks for the question. So this is our initial point. This is like given. So this is not obtained. So
Okay.
this is not obtained by the algorithm. Okay.
It's
So
given.
this is not obtained. By the algorithm. For example, in PyTorch, we have some simple initialization algorithm. We have played with it. So for example, we can use, Chi-mean initialization, initialize all the weights to some uniform distribution, and with a certain variance. So that's our initial point. Okay, so it's our initial guess or what we want to name it. But this is not obtained by the algorithm. But starting from x, the first iterate. Okay, so we'll start. So once we start our algorithm, so this one, the first iterate will be obtained by the gradient descent algorithm. So this one is pre-specified. Okay. So then we have local convergence, and this is more. So this is more of a more practical, and in most real life situations, we only have local convergence. The reason is choosing the correct step size is sometimes too expensive. We'll see. So local convergence means, okay, so there exists, okay, so there exists a delta that is greater than 0, okay, for any x 0 in a small neighborhood. For any x0 in a small neighborhood of our local minimizer, we have x kth iterate converges to x star as k goes to infinity. So if we use plain English language to translate this mathematical symbol, so there exists a delta that is greater than 0 for any initial guess that's in this neighborhood. This converges, it just means our algorithm converges when our initial guess is sufficiently near. So converges when our initial guess is sufficiently close to our local minimizer. Okay. So next is the rate of convergence. Right. Okay. So next topic. So next, or say next thing we're interested in study the convergence is the rate of convergence. So the rate of convergence is the following. The rate of convergence is if we can show a bound like this, if we can show, so again, x star is our local minimizer that we want to get to. Okay, so what is this? And what is this? Okay, so if we have a norm, think about it. So if we have a norm, so if this is the norm, then x subtract y can be interpreted as the distance between x and y, 2 points. Okay. So this is the distance of the current iterate to the local minimizer. All right. So this is what? This is after we run gradient algorithm for an iteration. This is our distance, like the next iterate. The distance of the next iterate, which is x k plus 1 to x star. Okay. What we want to achieve is this guy is closer to x star. This guy is closer to x star than this guy. It's distance to x star. Okay. So how do we quantify closer? That is, this guy is strictly less than rho. Rho has to be what?
Less?
Less than what?
Between 0 and 1.
Yes. Rho is something like this. Okay. So this is our hope.
Oh, yeah. Okay. I was just wondering if you'd really want to include 0, but I guess, yeah, if you hit your local minimum, then yeah, rho would be 0. You're good. Okay.
So this is our hope. Okay. And if we can have such an inequality, so which we will show, we will choose the step size alpha so that this is cool, and rho is called the rate of convergence. For a linear convergence. Why we call linear? Okay. So actually, we have, so given rho is from 0 to 1, so this power p here, okay. So we have three cases. If p is 1, we call this convergence linear. If p is greater than 1, we call it superlinear. So for example, if p is 2, we call this convergence quadratic. And if p is less than 1, we call this sublinear. And in all, I'm saying all, in all machine learning algorithm, first order, so we'll learn order as well later. It's all in the sublinear region. So if we can hit linear, you know, so you get a prize for that.
I have a question. Like, why we divide linear? Linear means P is equal
It's
to
a
1,
definition. So the reason it's called linear is by definition. So
if P is greater than 1, then is can be nonlinear form?
oh, okay. So I see where this question is. So this linear, this term is not about linear versus non-linear. Okay, so the rate of convergence being linear is we can think like this is order 1.
Yes.
Okay. So why people like to call this linear is because when we plot, so think about, we have a sequence. So if we define, okay, so I think this lady's question is why it's linear. So when it's non-linear, the answer is if p is less than 1 and p is greater than 1, they are non-linear. But it's not about linear versus non-linear. This linear means the rate of convergence, or say the convergence of the order 1. Why it's order 1 is, so think about so if we have done a machine learning project, we like to plot our convergence plot in semi-log y or log scale, you know, if we call a package such as matplotlib, and or we use MATLAB, okay? So why? It's because we define, so let, okay, epsilon sub k is, so if we let this, okay, if we let this, and if that inequality is true, we can do something like we let, and this is our hope, okay? So then what we can do is, so let me still use rho, okay? For what? This is, so if we think about this, okay, this is a geometric series we learned in calculus or even in high school. Okay, so this actually implies what? This actually implies epsilon k is a geometric series, okay, because this is rho square, epsilon k minus 1 equals rho cubed times epsilon k minus 2, etc. So this is epsilon to the kth power, okay? And this is some epsilon 0.
I think it's also important to point out that that's rho and that's
Oh,
p.
yeah, okay.
Maybe, in your top line up there, I think it's also important to note that
It's rho K. This is rho K.
Well, I'm not talking about your top line up
The
there.
top line.
You got less than rho xk minus x star raised to the p. That's rho and p. So those are different variables. Those are not the same variables.
Okay.
Rho is.
Yeah, here I'm just demonstrating.
Yeah.
Demonstrating why it's called linear.
Yeah.
Okay.
But imagine what would be if p is greater than 1, then if x minus x bar is less than 1, then the closer you get, the faster you get there more closely because you're squaring a number less than, or.
That's
yeah.
true, yeah.
Yeah, but if it's less than 1, you're taking the root, so you're wider, so you better hope your rho is really small. So you can, so think about that if that norm is less than 1, what p does to that. If p is greater than 1, you're going to accelerate your learning. If it's greater than 1, but if it's less than 1, you're going to decelerate.
No. It's still accelerating, just accelerating in a.
Well, that's true. Less in a lesser fashion. Yeah.
So if the p and the rho are different in your is that p like less than
Oh,
1?
maybe I shouldn't use p. I see where the
Yeah.
confusion is.
I think that's the issue. Is that those look the same? You got rho and yeah.
Okay, so let me change this to, because it's normally LP, and we use rho as
Similar.
yeah. Let me change this to beta.
Yeah. And now think about, like I said, if xk minus x star is less than 1, what that beta does to that. I mean, if you're less than 1, you've got the way that sizes that. Yeah, 1 is you're just going to come down on a nice straight line, but if it's like 2 or 3, you're gonna fly in there pretty fast. Because
So if beta is 0, does it fit into the beta is less than 1 case as well? Or is beta equal to 0? Oh wait, never mind, because never mind. I was
Beta has
confused.
to
I never
beta
mind.
has to
We're
be
good, we're
close. Beta has to be greater than 0.
good. Yep, okay, we're great. Thank you.
Okay. So then we have this geometric series. If we take log, so we take log. All right. So this is a linear function in the iteration number. Okay, so that's why it's called linear convergence. It's because in the log scale, our error decreases in the linear fashion.
okay.
So that's why. So when you've done a machine learning project, everything is sublinear, because if we use stochastic gradient descent, you'll see something like this, But overall, our convergence looks like this in the semi-log or log-log scale. If it's linear, our algorithm would look like this. Like I said, if you have discovered a first-order algorithm that looks like that, then you'll be getting a prize. So in the rest of today's class and next class, what we will learn is what the rest topic is, how to choose alpha k for this simple problem. So we have linear convergence. this is our topic and how to prove it, and how. And how to prove it. Okay. So this is our goal. So we did lots of preparation. So I could perfectly write this, in the first minute of our class, but then it will be confusing. Okay, what is that? What is this? Okay. So this is our goal. So once we know what our goal is, interesting. They add a Wi-Fi signal amplifier here. Cool. So once we know what our goal is, okay, so we'll introduce a new methodology called line search. Okay. What does it mean by line search? Is we can use this simple example. Again, I want to remind every one of us, this is the analog of a quadratic function in high dimension. Okay. So we can always fall back to the one dimension to illustrate what our function looks like. For example, our function looks like a quadratic function in 1D, so this is our f. And for example, if this is our current iterate, all right? And we know that this is our x star, which is the minimum of this quadratic function, all right? And if we take gradient of this quadratic function at this point, so we'll get the slope, right? So this is negative gradient of f. And this is our current function value. So let's think about the following problem. Given this, we can think this is our initial guess even. So from here, from the current iterate to the local minimum, okay? So if we can find how far they are, we've solved the minimization problem, because we need to step in this direction. This is a negative gradient direction. We need to step in the negative gradient direction with this optimal step size. Then we get to the minimum. Okay. So the line search is to formulate this heuristics into a formula. So what does line search mean? Is we define a function, okay, that is a function of the step size, or say learning rate. It evaluates the function value along the line. Why it's called a line is because we follow the direction of negative gradient. Okay, we follow it, then it's a line. So it is I mean, this is not technically where our next iterate is, because it's a function of alpha, and this phi is a function of k, because it depends on where our point is. So this is what? This is function value. along the line in the direction of the negative gradient at the current iterator. Okay? So what does a line search means? We search a step size. So line search method is we want to solve, so we solve for an alpha. So this is like the optimized or optimum step size. That is, we solve the following problem. Okay. We find the minimum among all possible step size that this guy is minimum. That this phi alpha k, okay, is a minimum. Okay?
But it doesn't guarantee like that if that doesn't exceed the distance like from the step that we are in the minimum local, right?
That's right. So, okay, so let me rephrase this gentleman's question. Okay, so we want to find exactly this step size, not bigger, not smaller. Okay, so this is our goal. But I have to be pessimistic about this goal is because this problem. Okay, so this problem, like there is a famous no free lunch theorem in every applied math subject, optimization, machine learning. You know, the bad news about this problem for general f, okay, the difficulty of this problem is equivalent to the original problem. So we just formulate the original problem we want to solve in another form. We didn't solve the original problem. For general f, this is as difficult as the original. Okay. So, however, we're in a good shape because we limit ourselves, you know, considering an egg in the vacuum, which is the quadratic function in high dimension. So the good news is we solve problem. So we solve problem. Let's call this problem capital L. So we solve capital L for what? For this quadratic function. So if we have, so let's take the gradient for this. So let's recall, okay. First order necessary condition. So first order necessary condition says we want to find a point such that for all admissible, this is greater than 0. Okay. Second order necessary condition for x star to be a local minimum is a Hessian, right? It's positive. a lambda minimum, or the minimum eigenvalue of the Hessian matrix at the current iterate is positive. So what we'll consider is second order sufficient condition here. The second order sufficient condition says the following, that is, the gradient of f, okay, is 0. So we have a critical point, and I think this is greater than 0, necessary condition. Sufficient is strictly positive. So we'll use the last one, because once we have found the point, okay, so once we have found the point x star that satisfy these two conditions, okay, we can safely say, oh, we have found our local minimum. Now let's try to solve the condition. Let's try to solve the condition for this function. Okay. So now let's we're going to simplify this. Okay. So Q. So for example, we want to take the derivative of x for this. Let me check the time. Yeah, I'll directly give you guys a formula, but if you want to see the derivation, you can refer to the notes. The idea is basically, because of this is x transpose qx can be rewritten as the sum of all possible ij combination, and this is xi, qij, xj, okay?
What is the symbol?
Say it again.
Is that Q? QIZ?
Yeah, this is qij. It's a little qij. So capital Q is a square matrix, n by n matrix. This is Q11, Q12, Q1n, Qn1, Qn2, Qn. So it's a square matrix with indices Qij, and okay. So once we take derivative with respect to I or j, we'll see, we'll get rid of one of those, and we are left with this, summing up. Then what we will get is the matrix multiplication. Okay, and then we'll use the symmetricity of Q, because Qij is Qji. So we'll have two copies of the term that will cancel with this 1/2. Okay. So if we use this formula, we'll get a very nice formula of gradient of f. That is q multiplied with x subtract. Okay.
Is that BZ? The last part minus.
Easy. Like I said, if you are not comfortable with n-dimensional formula, we can always use one-dimensional formula. So this is like taking derivative of this function with respect to x. And then we change everything back to negative. And its Hessian is even more simpler. Its Hessian is just the q. And we know q is SPD, so we restrict ourselves with a Q positive. So this means what? The second condition is automatically satisfied. Okay. So second condition in SOSC, second order sufficient condition is automatically satisfied. It's satisfied for any iterator. Okay. So this is a very strong condition, and later when we do the analysis next class, so we have a name for this condition. This condition has a name. This condition is called strong convexity. So if you're interviewed for a job for machine learning, and if your interviewer asks you what strong convexity is, and in an optimization problem, you can give him or her this answer using a quadratic function. So, and now what we try to solve is, once we have this, okay, so we can see that for QSPD, okay, so the minimization of this is equivalent to this problem. So we want to find our x to be our local minimizer of this function is equivalent to, we solve, okay, think about this. This condition is automatically satisfied. Now we need, this first condition is equivalent to solve x in qx subtract b is 0 or qx equals b. Why we don't solve this? So in fact, if we have played with earlier packages such as scikit-learn, actually scikit-learn, even for scikit-learn, earlier packages like scikit-learn solve a linear regression problem. They don't solve this. They don't solve this system. So there's an answer to that. For example, so this is a common interview problem in machine learning. Why don't we do this for gradient descent? The reason is because this is too expensive. Okay. So a solver even to approximate this, but this is beyond the scope of our class, but it's good to know. Okay, so even the state-of-the-art solver for Q inverse, it takes n cube, big O of n cube that time to do that. Okay, and n is our dimension, or n is our number of variables or number of features, whatever we like to call, in a linear regression. I mean, we can do a simple calculation. So we can do a simple calculation. For example, for a supercomputer, it takes, for example, 1 second. So this is like a simple problem to compute for us to entertain ourselves. So if it takes the supercomputer 1 second to complete an operation of an order n algorithm with n equals maybe, I don't know, 10 million. It takes how many seconds to do an order n cube algorithm? The same algorithm for n equals 10. You guys can compute. It takes perhaps I don't know. You guys can compute. This is not too bad. It's literally compute like we take cube, okay, and then we compute the seconds. But I doubt it's perhaps more than, I don't know, maybe 1,000 years. I haven't computed this, but you guys can compute. So this is bad. Okay. So the reason we don't do this is expensive. So instead, we want to solve alpha, okay, in the following problem. Okay. For general f, this has nested. This is like gradient of f nested with f itself. We have the composition of two super complicated functions over back. But for our quadratic function, it's not that bad. It's because we have an explicit formula for the gradient. And this actually has a name. So this actually has a name in the context of iterative solvers for optimization problems. This is called the residual of the normal equation. So it's not that bad. It's this guy. Okay. So once we denote, G superscript of k equals the gradient of f at iterate kth iterate equals this guy. Let's see if I can finish the derivation. What we want to do is we want to minimize a quadratic function. We plug it in, okay? So phi k of alpha is then 1/2 so xk subtract alpha gk, okay, transpose q xk subtract alpha gk subtract b times b transpose times x. X is x superscript k subtract alpha gk. I want to remind us that this is a function. This is a function with only one variable, a single variable. That is our step size. That is alpha. And if we think about this, this is actually a quadratic function of alpha. Let's simplify this. So this actually has, let's don't skip the algebra. So for example, we multiply this q here. So what we will get is x k iterate transpose multiply with q x k iterate subtract. This alpha is a scalar, so it can move freely in front of everyone. So now our key is to simplify the first term. And what we can do is, for example, so again, what we can do is we use a technique called FOIL that we learned back in middle school. So for example, the first term, what we will get is xk transpose q xk. This is the first term. Second term is this guy. That is subtract alpha xk transpose q gk. The next term is subtract alpha gkq transpose xk. And last term is plus alpha squared gk transpose q gk. So this is the first quadratic term. And I do, that is these two are the same. So these two are equal. It's because, first of all, these two are scalars. Okay. So these two are scalars at the first place. So these two are scalars, which means if we take the transpose of it, if we take the transpose of the first scalar, we should get the value of x. But if we take the transpose, it will become gk transpose q transpose xk transpose, then x, then transpose, so we'll get back to xk itself. And q is symmetric. Okay, so this guy, because it's a scalar, so it's transpose itself, but if we take the transpose, we apply the formula and the symmetricity of q, we get this term. So these two are the same. And so this equals 1/2 xk transpose q xk subtract, so 2 alpha cancel with this 1/2. Okay. So this is xk transpose. So without loss of generality, let's let's use this, okay? All right. So by the way, we don't have to know, I mean, this all derivation procedure, so we gotta know how to use them. Okay. So we have this, and then we have this term. Now we take derivative of alpha. So this is a function of alpha. Think about this. So even though it has a long, long expression, it's not a function of xk, it's a function of alpha. This is a function of alpha. This equals phi k of alpha. What we want to do is we take derivative of alpha. Okay? So if we take derivative of alpha, the first term has nothing to do with alpha. So nothing to do with alpha. We do have to consider this term. We do have to consider this term. This has nothing to do with alpha. We do have to consider this term. So what we obtain is, so if we take derivative of alpha, we have negative g k transpose q xk. Okay. And then, so this becomes, so alpha, 1/2 alpha, it becomes plus alpha gk transpose q gk. And this becomes plus b transpose gk. Okay. We set this to be 0. So it's alpha gk transpose q gk equals, so we move these two terms to the right hand side, we'll get gk transpose q xk subtract b transpose gk. Oh. Yeah, I should write, then I should write this as gk transpose b. So we'll repeat part of this. And then the right-hand side, the most amazing part of the right-hand side, when we pull out this gk transpose, this is gk. So the optimum alpha for the quadratic function is gk transpose, because this is a scalar. So we'll repeat part of the derivation next time, is gk transpose times gk divided by this number. So this is our optimal alpha. So we'll stop it here, but we'll repeat part of the derivation next time. So this is optimal step size for the quadratic function. So actually in 1D, we'll reach to the minimum in one step, but in ND, you know, it's a different story.
Thank you.
হোমওয়ার্ক ফিনিশ করেছেন?
হুম
হোমওয়ার্ক
দুইটা কমপ্লিট করছি আর দুইটা
পরেরগুলা?
দুইটাগুলো বাকি আছে চার
আরো দুটো বাকি আছে? বাপরে।
4 আর 5টা বাকি আছে
Quick question about biomagnetic.